So, very warm welcome from our side to our webinar, and with the topic of multi-component analysis with Raman spectroscopy and Raman matrix, and the focus is on Raman matrix, and we would like to show you how easy it is to analyze Raman data with a very user-friendly tool, with all the steps are necessary to come from the data to the information or to the result. So that's the main topic for today, and the example is, as I already mentioned, multi-component analysis and a quantitative approach for that. So before we start, I would like to introduce your hosts. This is Olivia. She will care about all the technical things that the chat would or will run quite good, and everything that is needed to have the most out from our webinar. And the other one is Oleg. He will present the Raman matrix and go through a live demo with Raman matrix. And the third, this is me. I'm Jörg, and I will give a short introduction to biophotonics diagnostics, that you know who we are, and then hand over to the topic for today. Yeah, there are some organizational things. We will record this webinar. Any personal info that may come up during the webinar, we will blind so that we are possible to give you access to the recorded webinar, so that you can have a look again later on and see some details again. So yeah, the second point I would like to introduce or to show what's the schedule of today. So for that, I will show you what we would like to do today. Yeah. At the beginning, as I already mentioned, the introduction to the biophotonics diagnostics. Then you will get an introduction into the Raman matrix, our software tool for analyzing Raman spectroscopy data. And then you can see how it works in a live demo at our example of quantitative analysis of a multi-component study. And at the end, there is a lot of time to give us your questions, and so that we can answer everything you are interested in. And to give us comments during the webinar or for the question and answer section, please use the chat functionality of Teams, so that we can get your comments and questions and can react on. Yeah, this is the very simple introduction. Then some words to the biophotonics diagnostics. Biophotonics, I forgot. We have included two questions to you, that we can have a picture of your professional field in all overall that you of our participants today. So the first question we would like to give you now, and Olivia is activating it. It's the question, in which field do you work? And after that, we can see the results, a summary. So please check your main field of your professional work, please. So answers are coming in. So yeah, and I think we have quite good overview right now. The main field is with approximately 30% process analytics. Biology is with 24%, also quite large field. And then chemistry and applied physics is with 12%, and 6% is optical design and engineering and quality control. Okay, are there some more? Oh yeah, medicine and others also 6%. Okay, thank you very much for your answers. So then I will switch to the presentation again. So yeah, the Biophotonics Diagnostics is a spin-off of the Leibniz Institute of Photonic Technology. It's located in Germany, in the town Jena. And our background is a broad knowledge of Raman technology and its applications because of this history. A lot of scientists were working on Raman spectroscopic projects, and all the needs, all the experiences entered the design and the functionality of the RAMANMETRIX software. Yeah, what we offer to our users and customers, that is on the one hand side, the RAMANMETRIX in the kind of licenses, online version and desktop version, and on the other hand side, complete support for solutions with Raman spectroscopic technology, and on the way from left to right, there are different possibilities with training, for example, or coaching in application-specific model building, for example, and also support in setting up measurement procedures or databases where the analysis is based on and modeling is based on later. Yeah, and especially for the RAMANMETRIX, there's one software package now, but if there are needs to design specific user interfaces or integration in different spectrometer software or diagnostic devices, and also special databases or specific application algorithms, then we can support you, and so that you get the best out of your Raman spectras. And the last part of my introduction is just a first overview of the functionality blocks of the RAMANMETRIX, and what you will see is the more the upper part today, how to build a model, how to test it, and so on, and everything that is needed for that. And for routine analysis with live data, for example, there's also the opportunity to use the Raman backend for automatic analysis with an already built model, for example, so that you get your live data in and gets the results out with the machine learning analysis process. So, and this is what I wanted to show you in principle at the beginning. And then before we come to the RAMANMETRIX part that will presented by Oleg, we have the second question for you. And in the field of data analysis, what is your main need or your main field where you for what you use data analysis? So please answer that question too, and then we will see how it looks like with our today audience. So at the moment, yeah, there are some answers coming in. So here, it is the most field are the quantification and the classification tasks in data analysis, data preprocessing, very important part here with 20%, and model validation and others with 7% each. Okay, thank you very much. So then I would like to hand over to Oleg.
Yes, thank you for introduction and already giving some idea about today's presentation. And first I will start with conceptual things about data analysis and specifically about multiple response regression and of course specifically for Raman spectroscopy. So sorry for the screen. Yes. So today I will mostly talk about partial least squares regression, and I will mention such algorithms as PLS1, PLS2, as well as PLS2DA. So specifically for multiple response, we will be using PLS2. And to describe the general pipeline of Raman spectroscopic data analysis, I did this really oversimplified slide for the whole preprocessing routine and data analysis routine, which starts from data pretreatment that is aimed to standardize data relatively to measurement device, and then preprocessing to remove corrupting effects related to the effects coming from the sample itself, such as fluorescence, for example. Then we also have quality check, and only after that we have typically dimension reduction and supervised or unsupervised machine learning. So basically, I will mostly focus today on the model building for multiple regression case, but I will also shortly mention the classification and what other possibilities are there. So first of all, we have different types of statistical models. It's clustering, classification, and regression. And today we will focus mostly on the regression, which means that we have certain observations and we want to build a model that will give us a prediction of some continuous response. So for example, concentration that is measured. And other methods are classification and clustering. And it's important to understand that from the machine learning perspective, classification and regression are sometimes taken care of using the same exact models with just slightly different decision making. So for example, if we are looking at the regression models in the RAMANMETRIX, we have quite a few regression models, and you can also combine them with different dimension reduction techniques. However, for partial least square regression, doesn't matter if you are using PLS1 or PLS2, additional dimensional reduction is typically not required because PLS is a dimension reduction technique itself, but it is a supervised dimension reduction technique. So what does it mean? It means that it constructs the components of features that represent your response, numeric response typically, in the best possible way. And in case of PLS1 algorithm, you only have a single response. So for example, you can predict a single concentration. And PLS2 is quite similar actually to the PLS1. The main difference is that you can provide multiple responses, multiple continuous responses. So you can at the same time predict multiple concentrations by using the exact same model. So which makes it slightly more consistent and also allows you to track some dependencies within your data set, which might not be easy to reflect when you use a single response only. So why I was also mentioning the classification algorithms is because this PLS2 algorithm could also be used for classification models. In that case, instead of providing numeric responses, here it would be simply a dummy matrix with zeros as one, representing, for example, 3 different classes, with one representing positive class and zeros representing information that this observation does not belong to a specific class. Yeah, but today we're only focusing on PLS2 as a regression technique for multiple responses. So for example, multiple concentrations. And the way we do machine learning part is that we perform training of the model. And here we have to provide regression responses in case of regression models. In case of classification, it would be class labels. And then we perform cross-validation of the trained model in order to validate how well does it perform, and as well optimize the number of features that we want to use in our final model. So following this cross-validation, we can select the best model and apply it to the unknown or independent data subset to get a good idea of how well the model will perform in real-life application. So the way we perform this cross-validation is simply by splitting our training data into different folds or batches, and then within each split, we take out one validation fold or batch. We put aside and build multiple models with different number of components used. And we apply that model on the validation fold, which was taken out at the beginning. This way you can get prediction for all observations in your training data, but at the same time, none of the predicted data was included originally in the training data. That's why you can reliably optimize the number of features for your training data set. In case of partial least square regression, those features are called latent variables. That's why it's written here LV, but it's often also referred as just components or partial least square components. Yes, so now coming closer to the actual application part, how do we actually perform this kind of analysis? So I switched to the RAMANMETRIX software, which already was introduced nicely. And how do we perform the training? In this case, we simply load the training data, and I will load the data collected from the bioreactor from two independent runs of bioreactor. So they're here labeled as runs 3 and 5. So we put them together in a single zip file. And when we load the data straight away, you see some warnings, which are actually meant to help users validate if the data represent what they expect. So in our cases, we just know originally that we don't have all data labels that were desired. So for example, we don't have optical density measured for some observations, and we don't have one of the concentrations measured for all observations. And in our case, those warnings are actually expected. But if you see warnings that are not expected, that's a sign that maybe data was not parsed correctly, or it was not structured correctly in the first place. That's why it also helps you to verify if the loaded data is displayed correctly. Yes, and straight after loading, you see measurements from different time points, so in different runs. So this is runs 3 and 5, for example, and multiple samples measured per run. So the simplest way to run through the data analysis is just by clicking Analyze, and then it will perform all the steps. In my case, I already pre-selected the parameters for this particular analysis and pre-processing, but generally you have great flexibility in adjusting parameters. So for example, now we have quite average expertise level, so you don't see all the parameters, but if you increase the expertise level, you can see that more parameters become available to you. And yeah, we have quite a few pre-processing steps and pre-treatment steps for the data. It starts from despiking, which is removal of cosmic spikes in our data. In case of this particular data set, we don't see that issue dramatically. That's why I cannot really show you where the spikes were removed, because we did not have them in the first place. However, the next step is calibration, and This is one of the most important steps. Even if you do not have calibration data, it is important to interpolate your data set on the same wave number axis. And it's especially helpful if you have measurements from different days when device was calibrated differently. So it actually can be still used with our software because we interpolate everything onto the same wave number axis. So those two steps are actually part of data pretreatment. So part of the device-related effect suppression, but then we have also pre-processing to remove the fluorescence background by baseline correction. In this case, it's used SNP baseline correction, but we also have another option for model-based pre-processing. And after the baseline correction, we also do normalization of the spectra, in this case to L1 norm of the spectra. And for this particular data set, we did not have too much outliers. That's why we also don't do the quality control check, but that's also an option that you can enable if you need to. Yeah. So going to the most important part for today is actually the multiple regression. And as I was explaining before, we are using PLS2 model, which allows you to use multiple responses. So in our data set, we have quite a few numeric responses which we can use. So those are 3 acids, ethanol, glycerol, and 2 products. So those are all concentrations. We also have optical density and time, but we are not interested in modeling it. However, if you remember from the beginning, we have a warning that we don't have all the observations for acid 1. That's why we're also not including it. And we can, however, select the responses that we are mostly interested in. So I have selected those 4, and those are acid, 3, ethanol, glycerol, and one of the products, just as an example. And we also have to select what would we consider as a main response. So the response that will be used to optimize the number of used components. In this case, I just select the acid. So when we construct the model, we optimize our number of components between 1 and 15. And here we get the answer that the optimal number of components for acid 3 is 4. And we can also see the statistics on how well does model perform on all the responses. You can see quite high statistical significance, so it's always above 0.9 for all the models. But of course, it's best for the substance that we used for model optimization. And for this particular substance, we also see the results and the regression plot, which does not look perfect, I would say, but the important thing is how does it perform in testing. So what we can do, we can load our test data. In our case, this is run 6, which was not included in training in any way. So this is independent data subset. And by a single click, we obtain the predictions for this independent run. Here you can also see that predictions are actually quite good for all our predicted substances through the statistical significance. And for a particular response, which is one of the acids, we also have quite high correlation between the reference value and the predicted values. Here, you can also see it in the regression plot that it gets slightly off for higher concentrations, but generally it's very linear and quite representative for the data set. So now, of course, we can go further and analyze what different concentrations look like, or analyze the PLS coefficients to make sense if that particular model is meaningful, and if the peaks which we've seen in our model coefficients are actually representing the specific substances which we are interested in. But that's topic of a larger discussion, I would say. And today I would rather demonstrate how to apply this newly built model in close to real life application. So what we can do, we can export the model and save it somewhere. So I already have some model saved here, but let's save another one. Just for demonstration. And now we can already close the RAMANMETRIX software itself. And I will show you kind of toy example of how this model can be integrated in the actual software or measurement software, for example. So this is just a dummy replica of a software measurement device. So what this small tool does, it watches the folder, and whenever we have spectra added to that folder, it will start predicting them. But first of all, we need to connect this tool to the RAMANMETRIX, and in this case, we just connect it to the RAMANMETRIX backend, which lays here in my user folder, and it listens to all requests sent to the local host. So basically what this software does, it watches this folder, applies the model, and sends it to the RAMANMETRIX backend. When we start with predictions, we basically don't see any results at first because we don't have files in our watched directory yet. So let me just use this space a little bit more efficiently on my screen. Yes. So basically this is a watched folder, and as soon as we started to add the files into the folder, we instantly see the predictions appearing. And on the x-axis, you basically just see the seconds from the start of the predictions. And whenever we add more files, you have more and more predictions. So just to speed it up, I will move all the files to this new folder. And then you can see that the predictions are going. And in this particular case, it moves rather slowly because we have set up the sleep time. So to simulate the actual measurement, but just to demonstrate that the software actually works much faster than that, I will set it to 0 and restart the predictions. So that's basically the speed with which you can get the responses in real life, which is much, much higher than normal acquisition time for Raman spectroscopy. And you can basically get your predictions in real life for all these multiple substances whenever they are getting measured. And this is just an example tool, so it can be integrated in pretty much any software, which we have described in our documentation, also on our website for documentation of RAMANMETRIX EU. So if you simply go here to Tools and Backend API, it basically describes how to use this prediction engine of RAMANMETRIX via HTTP requests to the running backend. But there are also other options, like, for example, loading it as a Python model. Then you can directly integrate it in the software, which works slightly faster, but cannot be combined directly with other programming languages. So then you have to stick to Python. But if you're writing your device specific software in whatever programming language you prefer, then you can also use this HTTP backend and send the requests directly to the running software. Yes, so that was a general overview how you can generate multiple responses model easily using RAMANMETRIX, and how you can integrate it with your proprietary software or your device-specific software for obtaining predictions in online measurement system. Yes. Thank you.
Okay, Oleg, thank you very much for your presentation. So, and now we have time to, answer questions, or if you have comments, just feel free to give us some things that are important for you. Yeah, use the chat functionality, please, and we are excited to see what are you interested in. So, do not see, is that right, Olivia? Yeah, it's the first question. Can we use RAMANMETRIX for FTIR data analysis?
Should I take Cora's answer?
Yeah, it would be good.
Yeah, so basically it is possible. As the main difference in the analysis would be that you should probably disable the spiking algorithm, because that would not be needed for FTIR. But otherwise, you can keep all other steps either intact, or maybe adjust also baseline correction to model-based preprocessing, like EMSC would be probably most suitable for FTIR. And otherwise, the preprocessing routine for Raman spectra and IR are quite similar. So yeah, you can generally use it. Just will be sensible to disable the spiking, because it will just take time, but it will not bring any benefit for IR data.
Okay, thank you. And then there's a second question. If you have a spectrum that is low in signal strength, do you have a method that takes care of it?
So I'm not exactly sure what is meant by takes care of it. So we have at calibration step, we have a smoothing algorithm which can add which can reduce the noise slightly. Besides that, we have smoothing at the first iteration of baseline correction using SNP algorithm, so to make it less noise sensitive. But also at the model step, if you apply such methods as PCA for dimension reduction, then typically PCA reduces so PCA reduces the noise in the first components, or considers noise less in the first components and mostly keeps the noise in the last components, which are mostly ignored by the model. And for the outlier detection, in our case, we call it quality control or quality check step, where you can set up the threshold for different parameters. So for example, you can select a specific peak intensity that should be in the specific range, or you can consider correlation with your reference spectrum as a quality parameter, as well as background intensity or signal to noise ratio. And also you have such filters as minimal or maximum intensity of the spectrum itself. So maybe it's easier if I shortly show the screen. So here you can, for example, select a specific peak. Right. Oh. So if you select a specific peak, then it would be possible to set up the intensities and of minimal and maximal intensity for that peak. But the other filters that you can use is a correlation with the reference spectrum. And if you don't provide reference spectrum, just the average of that spectrum is considered. So you can set thresholds, and you can also set threshold on the maximal background. And in that case, when you update your quality filters, you have spectra that passed quality filters or failed that quality check. And in your test data, if you have spectra that do not pass quality check, you also, we are already here at the testing step. So we have spectra that failed these quality check parameters passing, and those are not considered in the prediction. So basically they're excluded. And in our case, because I set pretty harsh thresholds, 30% were removed. And in the online predictions, those will also be excluded from the prediction. So about retriggering the measurement, it's completely up to you. So if you design software on your side that way that it should trigger the measurements, and you can set it up that way.
Okay, thank you. So are there other questions? There are no more at the moment. So maybe there's some that maybe come come a little bit later. So yeah, I will use this time to give you an idea what's happened after that webinar. As I already mentioned, we will send you the link to the webinar recording, so you can have a look on it again. And then, yeah, just take the chance and use the opportunity to contact us to ask other questions, and Olivia as our application specialist and Oleg as our data scientist can answer that, I think, very precisely. So yeah, just feel free to contact us for such things, and we will also contact you with the link of the webinar, so that you can, yeah, get a lot of information maybe after that. Okay, so there were no new questions coming in. So then we will thank you for your attention and for your attending to the webinar, and we are looking forward to see you again in the next webinar or in another conversation by email, for example. So have a nice day, and hopefully we see us soon. Okay, bye-bye.